Today we'll be doing the integral from 0 to 1 of the sine of the square root of negative ln x dx. And to start off, we will prove two identities. And we'll start off with gamma of k plus a half, the same thing as k plus a half minus 1 factorial, which is k minus a half factorial. So if we expand this, we're going to have k minus a half times k minus 3 halves times k minus 5 halves all the way to gamma of 1 half. But we know that this is the square root of pi. So we can rewrite this as 2k minus 1 times 2k minus 3 times 2k minus 5 times the square root of pi over 2 times 2 times 2 times 2. So we have a 2k minus 1 double factorial times the square root of pi over 2 to the k. So that's gamma of k plus 1 half. And we'll also show that 2k double factorial is the same thing as 2k times 2k minus 2 times 2k minus 4 times 2k minus 6. And we can rewrite this as 2k times 2 times k minus 1, and then 2 times k minus 2, and then 2 times k minus 3. So we're going to have a 2 times 2 times 2 times 2. So we're multiplying by k times. We're going to have a 2 to the k, and then we're going to have a k times k minus 1, and times k minus 2, k minus 3, dot, dot, dot. But this is just 2 to the k times k factorial. So now that we've shown these two things, now we could get started with the integral. So we had the integral from 0 to 1 of the sine of the square root negative ln x dx. And we'll make the substitution. We're going to let t equal the square root of negative ln x. But that means that t squared equals negative ln x. So negative t squared is ln x. E to the negative t squared equals x. Differentiating, we have dx is negative 2t. E to the negative t squared dt. The bounds of integration, t1, will be positive infinity, and t2 will be 0. So now using this, we're going to have the integral from infinity to 0 of the sine of t times negative 2t e to the minus t squared dt. And from here, we'll make another substitution. We're going to let s equal t squared. But that means that ds over 2t equals dt, and that the square root of s is equal to t, and the bounds of integration here do not change. So we're going to have the integral from infinity to 0 of the sine of the square root of s times negative 2t e to the negative s ds over 2t. And these two t's end up canceling, and we use this negative to flip the bounds of integration. So we're going to have the integral from 0 to infinity of e to the negative s times the sine of the square root of s ds. But we could rewrite sine of s to the 1 half as the sum from 0 to infinity negative 1 to the k, s to the 1 half to the 2k plus 1 power over 2k plus 1 factorial. So we're going to have the sum from 0 to infinity, negative 1 to the k, s to the k plus 1 half over 2k plus 1 factorial. So now plugging this in here, we're going to have the integral from 0 to infinity e to the negative s. Now the sum from 0 to infinity, negative 1 to the k, s to the k plus a half over 2k plus 1 factorial ds. And then swapping the sum and integration, we're going to have the sum from 0 to infinity, negative 1 to the k over 2k plus 1 factorial, and then the integral from 0 to infinity, e to the negative s times s to the k plus a half ds. And we know that gamma of x is the integral from 0 to infinity of s to the x minus 1 e to the negative s ds. So now comparing the exponents, we're going to have x minus 1 is k plus a half, adding 1 on both sides. This is just going to be k plus 3 halves. So we're going to have the sum from 0 to infinity, negative 1 to the k over 2k plus 1 factorial, and then gamma of k plus 3 halves. So now from here, we know that gamma of k plus 3 halves is the same thing as gamma of k plus a half plus 1. And using the properties of the gamma function, that's the same thing as k plus 1 half times gamma of k plus a half. So we're going to have the sum from 0 to infinity, negative 1 to the k over 2k plus 1 factorial. And we could rewrite this as 2k plus 1 over 2 times gamma of k plus a half. But using the identity we showed at the beginning, we said that gamma of k plus a half is the square root of pi 2k minus 1 double factorial over 2 to the k. So replacing that into the summand, we're going to have the sum from 0 to infinity, negative 1 to the k over 2k plus 1 factorial, 2k plus 1 over 2, square root of pi 2k minus 1 double factorial divided by 2 to the k. So we could rewrite this as the square root of pi over 2, sum from 0 to infinity, negative 1 to the k, 2k plus 1, 2k minus 1 double factorial divided by 2k plus 1 factorial times 2 to the k. And we could simplify 2k plus 1 over 2k plus 1 factorial as 2k plus 1 over 2k plus 1 times 2k factorial, but that cancels, so we're left with 1 over 2k factorial. So we're going to have square root of pi over 2, sum from 0 to infinity, negative 1 to the k times 1 over 2k factorial, and then we have 2k minus 1 double factorial over 2k. And now we're going to have to simplify 2k minus 1 double factorial over 2k factorial. So we have a 2k minus 1 double factorial divided by 2k factorial. This is going to be 2k minus 1 times 2k minus 3 times 2k minus 5 and so on over 2k times 2k minus 1 times 2k minus 2 times 2k minus 3 dot 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 times 2. And we see these 2k minus 1s cancel, these 2k minus 3s cancel, and this 2k minus 5 will end up canceling somewhere here. So we're just left with 1 over 2k times 2k minus 2, and then we have a 2k minus 4, and so on. But that's just a definition of 2k double factorial. But we showed in the beginning of the video, this is equal to 2 to the k power times k factorial. So now replacing that there, we're going to have square root of pi over 2 sum from 0 to infinity, negative 1 to the k. We're going to have a over 2 to the k, and then we're going to have a times 1 over 2 to the k times k factorial. So now simplifying some things, we're going to have the square root of pi over 2 sum from 0 to infinity. We're going to have a negative 1 to the k over, we're going to have a 2 to the k times 2 to the k, but it's just going to be 4 to the k times 1 over k factorial. This is equal to the square root of pi over 2. And then the sum from 0 to infinity, negative 1/4 to the k power over k factorial. But that's just the square root of pi over 2. E to the negative 1/4 power, which is equal to the square root of pi over 2 times 1 over the 4th root of e. So that is the final result to the integral. Thank you very much for watching.